In previous units, we discussed the sampling distribution. And in the last unit, we have seen that the properties of a sampling distribution of X bar help us estimate the range of likely values for a population mean mu. And this is the first inference method. And today we are going to discuss the second method. And we also rely on the properties of the sampling distribution. And what we do in this unit is to test a hypothesis. First of all, let's introduce an example. You are in charge of a quality control in your food company. You sample randomly 4 packs of cherry tomatoes. Those packs, each one is labeled as 0.5 pound, which is 227 grams. When we assume the population of the cherry potatoes has a standard deviation, sigma equals 5 grams. And once you randomly choose these 4 packs, you measure all of them, then you find the average, the mean of these 4 boxes equals 222. Actually, so this is the X bar, because the sample size equals 4, that is n equals 4, and the mean of the sample X bar equals 224. And sigma is the standard deviation for the population. Obviously, we cannot expect boxes filled with whole tomatoes to all weight exactly half pound. So the average equals 222. The individual box may have a different weight. Let's recall what we did in last unit. We can calculate the confidence interval. For example, for a confidence level, for example, C. And what we do is from this C, if we are given C, for example, equals 95%, and we can calculate the Z star from table D or from table A, if you like. And once we can determine this Z star. Once we know the Z star, because we already know the mean of the sample, so the inferred population mean is which can be represented by a confidence interval is X bar plus Z star times sigma divided by the square root of n. And this one equals X bar equals 222, and this one equals 1.96 if you look up table D. And sigma equals 5 and n equals 4. So plug into numbers, we get 222 plus and minus 4.9 grams with 95% confidence. So that is what we did in last unit. Now we are going to ask a different question. We know each box is labeled as 227, but our average of the sample equals 222. So this somewhat smaller weight, is this smaller weight simply due to the chance variation? Because we randomly choose this sample of 4 boxes. So is this due to the variations in chance? So that is the first one. Once we know the mean of this sample equals 222, is this evidence that the calibrating machine that sort cherry tomatoes into packs need a revision? We are not going to, for this question, we are not going to infer the population mean confidence interval. We are not going to do this. But the questions we are interested in is the first one, is this smaller sample mean just because of the chance variation? So that's the first question. The second question, do we need to revise the calibration machine? If the machine is wrong, then we need to recalibrate it. So this is the question we need to ask. Hypothesis. A test of statistical significance tests a specific hypothesis using sample data to decide on the validity of the hypothesis. So we need to use the sample data to test the validity of the hypothesis. So what is a hypothesis? In statistics, a hypothesis is an assumption or a theory, we don't know, about the characteristic of one or more variables in one or more population. This is the key, population. The hypothesis is a statement, is an assumption or a theory about the population. It's not about the sample, it's about the population. So in this example, what you want to know is, does the calibrating machine that sorts cherry of tomatoes into packs need revision? This same question can be reframed statistically. Is the population mean, mu, for the distribution of the weight of the cherry tomato package equal to 227? Because in the box we labeled it as 227. But our sample is 222. So we want to know from this 222, from this sample 222, can we infer that the mu equals 227? That is the question. We have another example. We assume the USM student's average GPA is 2.5. Now, we found that the average GPA of our class is 3.9. Our class. Here, we assume our class is a random sample. Maybe not, but we assume this is a random sample. Right? The question is this normal? Because we know that the average GPA of USM student equals 2.5, but we have a random sample as our class. The GPA, which is X bar here, equals 3.9. So is this normal? We can ask the same question, is this normal, in another way. We found that our mean equals 3.9 because this is a fact. We know that. This is a fact. We take the example, or we take the sample, then we measure it, and we calculate the mean equals 3.5. This is a fact. Can we conclude that the USM GPA equals 2.5? In the last unit, from here, we can calculate the confidence interval of the USM GPA. The USM GPA will be calculated by X bar, which is 3.9, plus or minus Z star, which is related to the confidence level, then times the standard deviation of the population GPA, then divided by the sample size, which is the size of our class. And we can get this confidence interval that is from last unit. But in this unit, what we are interested in is from this 3.9, can we conclude that the USM mean GPA equals 2.5? We do not care about this confidence interval. What we want is, we want to a statement if the mean GPA equals 2.5. Now we define some concept for several hypotheses. The first one is the null hypothesis. It is a very specific statement about a parameter of the population. So hypothesis is a statement, a specific statement about the population. Again, not about the sample. It is labeled by H0. the alternative hypothesis is more general. This is specific. This is more general statement about a parameter of the population, still applied to population, that is exclusive of the null hypothesis. That means this does not include the statement here, and it is labeled by HA, means alternative. In our example, the cherry tomato packs, the null hypothesis H0 is we want to know if the population mean equals 227. So our null hypothesis is mu equal to 227. This satisfies the concept. Okay? First one, this mu is a parameter about the population, not about the sample. Second, this statement is very specific. It is equal to 227. So that is H0. On the contrary, HA is also about the population. So we also said mu, but the statement is more general. It says not equals to 227. This one is a specific number. This one is not equals to 227. Maybe greater than 200, is larger than 227. Maybe smaller than 207. But it is exclusive. Does not include this. You cannot see greater or equal to 227. Or you cannot say this is less than or equal to 207. Anyway, we cannot include the hypothesis here, 227. So we can use this one, so great or less or not equal, but cannot be equal. The second example, the USM GPA, we know that the mean of the sample equals 3.9, and our null hypothesis is the mean GPA of the USM student body is 2.5. Again, this mu is applied to the population, and this is very specific. This is a number equals 2.5. And alternative hypothesis in here, we said the mu is greater than 2.5. So mu is larger. Definitely you can state another one. So mu is less than 2.5, or mu is less than 2.5, or you can state another one. So mu is not equal to 2.5. All these three work as an alternative hypothesis because it is more general. It's not equal to, or greater than, or less than. It's more general than H0, and also about the population, and does not include either one. Does not include the null hypothesis. Okay. As we mentioned here, we can see this one is not equal to, or we can choose greater than, or less than, or both. So this, we have two different tests. The first one is called one-sided test. The second one is called two-sided test. A two-sided test, also called two-tailed test. That means this null hypothesis can be greater than and can be less than. So H0 in this example, H0 mu must be a specific number, and HA is not equal to. That means can be less than, can be greater than, can be less than. Right? So that's two-sided. Let's do this one. Less than this and greater than this. So two-sided. Left-hand side and the right-hand side. So this is called two-tailed or two-sided test. A one-tailed or one-sided test of the population mean has this, like this. The mu, the same. H0 is the same. And HA, we can use less than. That means left-hand-sided. So one tail, left tail, or you can say greater than a specific number. Usually this specific number is the same as this specific number. Example is the FDA test whether a generic drug has an absorption extent similar to the non-absorption extent of the brand name drug, it is copied. And we know higher or lower absorption rate would both be problematic. So in this example, our test hypothesis, the null hypothesis H0 will be the mu, the mean of the generic drug equals the mu of the brand name drug. That's equal to. So this is a specific. And the alternative hypothesis is this one is not equal to, because we are interested in both higher and lower. So this is not equal to. So this one is a two-sided test. Next, we discuss very important concept. This is called Pvalue. Everybody studying statistics need to know this. The first very important concept, as we mentioned before, is the normal distribution. And the second one, I believe, is the Pvalue. In our example, the packaging process has a known standard deviation sigma equals 5 grams. We need to know the population standard deviation. The null and alternative hypotheses are mu equals 227. This is H0. And HA is mu is not equals 227. Why we want to use a two-sided test? The reason is if this one is the mu is greater than 227, then your company will not be happy. If the mu is less than 227, then the customers will not be happy. So either way, if it's greater than or less than, you need to revise your calibrating machine. So that's why we use a two-sided test. The average weight from your 4 random boxes is 222. Now we need to ask a question. So this is important. You ask this: what is the probability of drawing a random sample such as yours? As yours means the mean equals 222. If H0 is true, that means the mean of the population is indeed 227. Let me repeat this. You draw a random sample of 4 boxes, and you measure, we know the mean of the random sample equals 222. If we assume the population mean equals 227, what is the probability you get a random sample as yours, which the mean equals 222? What we are given here is the standard deviation of the population, which equals 5. And now you ask yourself, can you figure out how to do this question? Yes, we can, right? Okay, the first one, you calculate the z-score, because this is normal distribution. You calculate the z-score, then you calculate the probability. Because the population mean equals 227, yours is 222, then z-score is z-score equals here is x bar minus the mu equals sigma. Is this correct? Okay, no, this is not correct, because we are talking about the sampling distributions. So keep in mind, this has always there's a square root of n here. Once we calculate this score, then we check table A, we can find this probability. This probability is called the p-value. Test of statistical significance quantify the chance here, the probability. of obtaining a particular random sample result if the null hypothesis were true. The condition is the population mean is 227. And actually we use this fact to calculate this one. So here, this one equals 227. We assume this is true, then what is the chance we get a random sample whose mean is 222? We try to calculate this probability. And this chance is called the p-value. So it looks like we already know how to calculate p-value. Now, the most important part is we need to try to understand the meaning of p-value. This is a way of assessing the believability of the null hypothesis given the evidence provided by a random sample. Let's rephrase this here. Suppose the mean of the population equals 227. And the probability for us or for you to get a random sample whose mean equals 222. Suppose that chance or that probability equals 1%. That means it is not likely. If the population mean equals 227, you are unlikely to get a random sample like yours. Or if you calculate this probability equals, for example, equals 50%. That means if the population mean equals 227, you are likely to get a random sample whose mean equals 227. So anyway, this p-value is used to quantify the believability of the null hypothesis. Because here, the mean of the sample is true, because we know that 222 is true. If you think if the probability to get a sample like yours is very low, 1%, then where is the problem? The problem is your hypothesis that the population mean equals 227 may be not correct. But if this p-value equals 50%, that means very likely you get a random sample like yours. If the population mean equals 227, that means your null hypothesis is believable, is likely. Okay, we have another example. The odds of winning Powerball grand prize is 1 in 292 million. That is one example before. A random person, we assume this is you. A random person here won the jackpot. What is H0 here? What is HA? What is the p-value? Okay, first one, H0. H0 is a statement or assumption regarding the population. So here it said H0 is the chance to win a Powerball is 1 out of 292 something millions. What is the HA? HA is more general statement also regarding the population. You say, okay, in general, that probability is not equal to 292 something millions. What is the p-value? Okay, to answer this question, we need to go back to the conclusion. Go back to the definition. P-value means if your null hypothesis were true, what's the chance that you get a random sample like yours? In here, if the hypothesis which the odds of winning Powerball equals 1 out of this 292 million is true, then what is the chance that a random sample gets the result like this? Gets the result won the jackpot. Alright, so definitely this p-value equals 1 out of 292, 201,338. This is the chance. If this one is true, then a random person like you won the jackpot will have this little chance. We know that the null hypothesis and the sample statistic do not match all the time. That is true. In our example, the null hypothesis is mu equals 227. And our sample statistic, which is the mean of the sample, equals 222. These two do not match. The question you ask is, why these two don't match? Could random variation alone account for the difference between the null hypothesis and the observations from a random sample? Could the random variation alone account for this difference? For smaller p-value, and it implies that the random variation due to the sampling process alone is not likely to account for the observed difference. What does that mean? All right, we go back to the tomato example. If the population mean is 227 here, and the chance you get a random sample like yours is that p-value, right? If that p-value is too small, for example, only 1%, right? It's only 1%. So that means random variation due to the sampling process alone is not likely to account for the observed difference between 227 and 222. There must be something else. What is the something else? Well, the machine needs to be recalibrated. How about if this one p-value is very large, for example, 80%? If this one is 80%, that means the population mean equals 227, you are very likely to get a random sample like yours. So that is possible. So that may be just due to the variations between here and here is just because of the random variation. So we don't need to calibrate the machine. So here we see for small p-values is important. We cannot explain the difference between the null hypothesis and the random sample statistic with only the random variation. There must be something else. So if we get a smaller p-value, then our conclusion will be we are going to reject H0. We cannot accept H0. We need to reject. I want you to write exactly this word. For small p-value, then our conclusion is we reject H0, which means that the true property of the population is significantly different from what was stated in H0. Later time you're going to see we have a lot of wording, different wording, but you need to be very careful. For smaller p-value, our conclusion is reject H0. So small p-values are strong evidence to against or reject H0. So in the Powerball example, what is your conclusion? In the Powerball example, we said the p-value equals 1 out of 292 something millions. I believe this one is very small. It's much smaller than 1%. So we know the p-value is small. So what is your conclusion? with a smaller p-value, our conclusion is we reject H0. So we are going to reject H0. What is H0? H0 is the odds for anyone to win the Powerball is 1 out of 292 millions. So that means we reject that conclusion. We reject that statement. That means that it may not be true. Why that not be true? The reason is we select a random person and that person won the jackpot. So we don't believe the chance to win a Powerball equals 1 over 292 millions. If that is true, then a random person like you cannot, or the probability is very, very small to win the jackpot. Significant p-value. We have several diagrams here. The first one, the p-value equals 27.58%. The second one equals this is two-sided. The second one is one-sided, right-hand sided equals 17%. And the next one is two-sided equals 8.9%, and this one equals 7%, this one 5%, this equals 1%. The p-value means the, for example here, 1%. Two-sided means the area of this and this, the shaded area, equals 0.01. And this one is one-sided to the left. That means this area here equals 0.05. And this one, this both add up together equals 1%. So you can see here, this one is big, and this area is relatively large compared to the others. So that equals 0.2758. When the shaded area is small, like here, like here, like here, this one, because only 8%, this is 7%. So this and this, compared to this and this, those are small. The probability of drawing such a sample at random gets very slim. Because that probability equals very small. Oftentimes, a p-value of 5% or less is considered significant. The phenomenon observed is unlikely to be entirely due to the chance event from the random sampling. From here, usually when you draw the sample will be here. But if your sample is here, that chances is very small. It's very small, that means your sample is this phenomenon is very significant. And it is unlikely due to entirely the chance event from a random sample. We know when we take this sample, it is random. But the randomness alone cannot account for this small p-value, small probability. So this is a significant p-value. So p-value, when p-value is too small, it's called significant. And by convention, usually 5% or less, for example 1%, is considered significant. Sometimes 10% is also considered significant. Later time we are going to discuss how to treat this. Next, we are going to see how to test the null hypothesis. To test the null hypothesis, H0 mu equals mu0, a specific number based on a simple random sample of size n from a normal population with an unknown mean. This mean, mu is unknown. but we know the standard deviation. Size equals n, and this mu equals mu sub 0. We rely on the properties of the sampling distribution. We know the sampling distribution satisfies a normal distribution with a mean equals mu, and the standard deviation equals sigma over square root of n. The p-value, based on the definition, is the area under the sampling distribution for values at least as extreme in the direction of the alternative hypothesis as that of our random sample. Or maybe greater than, so that is to the right side. So less than, it will be to the left-hand side. If not equal to, then it will both sides. So how to do the testing? Right? First one, we calculate the z-score. The z-score equals x bar, because we already know the sample. In the tomato example, that is 222, so we know this. And mu is the H0. In our example, again, equals 227. And sigma equals 5, n equals 4. So we calculate this z-score first. Keep in mind here, only the absolute value of z matters. If you get z negative or get z positive, the sign doesn't matter. Actually, the value matters. So here, next time we are going to see why. So the p-value for one-sided test, HA, mu is greater than mu0, is z, the probability for z is greater than the z value. Z-score we calculate from there. We assume this one, no matter positive or negative, we always choose the positive. So greater than means to the right-hand side, so here. So this is the probability that z is greater than this absolute value. Okay. And if your one-sided test is on the left-hand side, mu is less than mu sub 0, then that is the probability. That probability it will be here. So this is the probability that z is less than, and we write a negative z absolute value. So make sure this one will be, because this score here must be a negative sign. This is in the middle. And this is always positive, this is always negative. So we guarantee with this v, negative absolute value, so this is negative. The p-value for two-sided test, it's gone here. Two-sided test will be this side and this side, so we are going to use a 2p because they are symmetric. This figure is symmetric, so we just use 2p greater than positive or 2p less than the negative. Next, we use the example to show how to do this. We go back to the tomato example. There's the packaging machine. Packaging machine need revision. Step 1, we state the null hypothesis and alternative hypothesis. So H0 is mu equals 227. Keep in mind, don't write mu equals 222. That one is not correct because 222 is the x bar. These hypotheses are always applied to the population, not to the sample. So mu equals 227 versus alternative hypothesis is mu is not equals to 227. This one, again, you cannot write 222. This number must be the same as this number, but is more general. This one is equal to, this one is not equal to. what is the probability of drawing a random sample such as yours? That means here, your x bar equals 222. What is the chance? What is the probability you get a random sample like this if H0 is true? When we calculate the p-value, we always keep in mind, we don't need to write this, but you always ask this question in your head. What is the probability of drawing a random sample like this if H0 is true? Ask this question always help to understand the question. Okay, now what we have is x bar equals 222, right? This sigma equals 5 and n equals 4. Then we calculate the z-score, and the z-score equals x bar here minus the mu and divided by sigma over square root of n, and that equals -2. -2 means here is -2, and then this one here will be equals 2. So z here equals 2. This one equals -2. And they are symmetric. So that's some textbook they may say, okay, this score is always positive. That means it's here. Right? But we use this to guarantee it is positive. We use the absolute value sign to guarantee this one is always positive. Sometimes they calculate this one, even this one, z-score equals -2, they still say the z-score equals +2. So I would like to use that absolute value sign to reduce the confusion. So z-score equals -2 here, but d equals 2 here. The p-value of the two-sided test is the area of this and this. Because they are symmetric, you can use this one or you can use this one. So I use 2 times probability z is greater than 2 here. So twice of this area. Later time, if you use some table that the probability given for the area from somewhere to the right, then you are going to use this one. But for our textbook, I believe the probability given is from here to here. So instead of this, a better way to do this is this one here, the p-value equals 2. The probability of z is less than -2. This is better. So if you look up table A for -2, you directly get this result, which equals 2.28%. Then you times 2, that equals 4.56%. But this one here is equal to this, the same thing. So we calculated the p-value, which equals 4.56. What does that mean? That means if the population mean equals 227, then we are going to have a 4.56% chance to get a random sample whose mean equals 222. Right? And this p-value is small compared to 5%. So this one is less than 5%. Here we use the convention. Sometimes if you are not given that one, we always use 5%. Because this p-value is less than 5%, we say this one is significant. Because the p-value is less than this one. Then our conclusion is that we need to reject H0. That means the population mean is not equals 227. So the machine does need recalibration. Okay, we summarize the steps how to do this testing of significance. The first one, step 1, we need to state the null hypothesis H0. Keep in mind, this one is regarding the population. and it must be specific. Then we need to state the alternative hypothesis HA. So that is step 1. Step 2, we need to calculate the value of the test statistic. The test statistic here actually means the z-score. We calculate this one. Once we know the z-score, we need to calculate the p-value. For p-value, we need to find, based on this one. So one-sided, left-sided, or right-sided, or two-sided. If one-sided, then we are going to use either left-hand-sided or right-hand-sided. We need to just use this one here. If two-sided, then we need to use these two multiplied by the each side. So calculate the p-value for observed data based on HA. It's one-sided or two-sided. Then the last step is we state the conclusion. We either reject H0 in favor of HA, or we do not reject H0. That means we failed, or another word is we failed to reject H0. We cannot reject. We never conclude we reject HA, or even we accept HA. Our conclusion is always on H0. We reject H0, or we failed to reject H0. That's all. Don't say we reject HA, we accept HA. All these are wrong.